Today's goal, the main goal, will be to introduce this induced electric field. What is that? We will naturally come to that point. Yeah, these are the sections. So what's the goal? So here's the form of the Faraday's law which we've been using, right? EMF equals to minus rate of change of the magnetic flux. There is nothing wrong with this law. It's a universal law, fundamental law, which can be applied at any point of the universe, at any moment of time, and it must work. So far, no one has found any examples where it would fail to work, right? Nothing wrong with this law, but this form of Faraday's law is usually is used by what? By technicians, engineers, applied physicists, but hardcore physicists, theoreticians, for example, they barely use Faraday's law in this form, right? Why? Because EMF, it's a very, very practical quantity, right? But again, mainly used by, as I said, technicians, engineers, and applied physicists, right? But not a hardcore physicist. They usually use what? They usually use fundamental quantities. What do I mean by fundamental quantities? Electric field and magnetic field. All right. Also, this is it's one of the equations in a set of Maxwell's equations, right? So basically, this equation forms like a foundation of electromagnetism, and foundation must be written in terms of, again, fundamental quantities. It must be written in terms of electric and magnetic field. Again, EMF, nothing wrong with EMF, with the potential difference. But again, it's a very practical quantity. And it doesn't consider it as fundamental quantity, right? Again, from the point of view of applications, EMF is much better, right? Much more useful to use than the electric field. But again, from the point of view of physics, it's better to write this fundamental law in terms of electric field and magnetic field. That's the main goal of today's class. We need to rewrite it in the most general form. Again, I'm emphasizing we're not introducing the new law, a new law. We're just rewriting Faraday's law in the most general form. And again, where is the magnetic field? Not a big deal. Magnetic field is inside of the magnetic flux. It's a B dot A. So pretty much we know where the magnetic field is. But electric field, we need to introduce, of course, electric field on this left-hand side of the equation. So we just need to rewrite EMF in terms of electric field. That's the goal of main goal of today's class. Right. Okay. So now. So how should we introduce this? As usual, right? What do we usually do in education, right? So usually we start from sort of a comfort zone where we are comfortable, with the stuff which we know, and move into the zone which is less comfortable for us, right? From the comfort zone to a less comfortable zone, right? And we work there until we'll start feeling comfortable, right? So now the same. Let's do the same here. Let's start with the example with which we are very familiar at this point. We should be very comfortable and move into a less comfortable zone. So we're going to make two additional steps. The first step will be kind of obvious. The second step will be far from being obvious. It will be even, I would say, counterintuitive. So at that point, you will have to trust me. But the first step is quite obvious. So let's start. Again, as I said, from the place where we quite comfortable. So let's assume that we have a uniform magnetic field, B external. Let's assume that we have some conducting loop, right? And of course, we can analyze, we're going to get induced current and what's the direction of the induced current. We've done this example many times. So at this point, we should be very comfortable. Okay, so let's assume that magnetic field, this B external, is increasing. You see, we have increasing uniform magnetic field. Right? So let's get direction of the current, induced current. Since flux is changing, of course, current will be produced. So let's just get the direction. As usual, Lenz's rule, 3 parameters. Area of the loop stays the same, angle constant, magnetic field changes. So as a result, actually not just changes, magnetic field increases. Magnetic field, okay, let's say increasing. Magnetic field is increasing. Of course, magnetic flux also increasing. So of course, the response of the loop is well known. So the loop rebels. And it will drive the current in such a direction so that the induced magnetic field will be in the opposite direction relative to the direction of the external magnetic field. So within the loop, as a result, I can draw a bunch of dots representing induced magnetic field. And now right-hand rule, dots, it means out of the board, so I have to position my hand like this. In order to get this direction towards us. And my thumb gives me, as a result, correct direction, which is counterclockwise direction. Right. As I said, it's at this point you should be quite comfortable doing all these steps, right? So as a result, induced current in a counterclockwise direction. So that's initial point. And now we need to make 2 additional steps. First question, if there is a current, there must be something which creates this current. Current usually consequence of something. What is that? Usually response of the students immediately because of the potential difference. Yes, that's true. That's usually, as I said, immediate response of the students. But that's what we have, potential difference in our current form of the Faraday's law, EMF, potential difference, right? But we want to move away from the potential difference. We want to move deeper into the description of this process. So what else must be sort of applied in order to get current in the conductor? Electric field. Electric field must be there, because what is effectively a current? Current, it's a drift of charges. Charges drift if you push them. In our case, what do we use to push these charges? Electric force. Electric force can appear only if there is an electric field, right? If this is, for example, positive charge, electric field that way, of course, electric force will be also that way, and charge will start drifting. We create current. So there are 2, we can say there are sort of, in order to produce electric field, we can say there must be potential difference or there must be an electric field. This over here, there must be an electric field. This electric field is called induced electric field. Induced electric field. It's a first step, which is kind of obvious, right? I don't have, after my speech, you should be convinced, right? So there must be electric field. And these electric field lines, these induced electric field lines, form circles. Why? Because you see, charges move around the circle, right? So at any point, for example, if at this point, charge must experience which force? Force along the tangential, right? So electric field, so force tangential, and of course electric field will be also in a tangential direction at any point. This point, that point, right? So at any point, electric field must be tangent to this loop. So electric field lines form circles. All right. So I can open up. Wait. So at this point, electric field is tangent. At this point, tangent. That point, tangent, 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 right? So electric field lines form circles. So it's a first step. That's why I put here Rome symbol 1, right? There must be induced electric field. And I emphasize, although I'm kind of lazy person, right? But you see, every time I keep pronouncing induced electric field, induced electric field. Before this, right, like at the beginning of the semester, every time I just used to say electric field, but now I keep adding induced electric field. And of course, it's a very important because, yeah, both of these, all of these fields, they're electric, but there are some differences. Some properties of this electric field are different relative to the electric field which we discussed, analyzed at the beginning of the semester. On the next slide, I will sort of juxtapose these two fields. This is an induced electric field. There are some different properties, although both of these fields are electric fields. All right. Okay, now the second step, as I promised to you, we're going to make two steps. And the second one is not intuitive at all. Okay, so we have a loop, we have a current, there is an electric field, right? Electric field lines are circles. Now, let's imagine this situation. What if I just grab this conducting loop and move it away from the magnetic field? What would be different? If I just grab this conducting loop and move it away from the system, would we have a current? Would we have the current, induced current? Of course not. Current will disappear because if there is no conducting loop, then where current can flow? Current can flow if there is a conductor, or in this case, conducting loop. So if I remove the conducting loop, current would definitely disappear. But what about the electric field, this induced electric field? This is the major point. Surprise, surprise, this induced electric field will be still there. Pretty much this whole space is filled with this induced electric field. And it doesn't matter if there is a conducting loop over here or not. This is not obvious. So you have to trust, right? So basically that's how God programmed the nature, right? So basically, changing in time here magnetic field produces this induced electric field. And induced electric field will be here, it doesn't matter if you have a conducting loop in the system or not. But of course, current can be only if there is a conducting loop, right? You understand? Current, it's a drift of charges. You must have charges, right? If you don't have charges in the system, then there's nothing to drift. Okay, so this step, as I promised to you, it's not obvious, right? So you just need to trust me, right? In this case, we can say that conducting loop, it's almost like a probe system. If somebody doesn't believe you, so that there is a electric field over here, you can just grab the conducting loop, put it here, right? And you can say, you see, there is a current flowing through the loop. Current can flow only if there is an electric field. So you see the current, so there must be an electric field. Or you can grab, you remember that small positive probe charge, position it, and of course the probe charge will give you a direction of the electric field. Position it at several spots in order to convince somebody that there is an electric field, right? But again, in order to produce this electric field, the loop is not needed, right? Okay, so we sort of introduced this induced electric field on a conceptual level, on the level of blah, blah, blah. But we still haven't reached the goal, because you remember what is our goal? To rewrite Faraday's law, to get rid of that EMF from the left-hand side of the Faraday's law. We haven't reached that, so now let's do that. So you need to understand, what are we trying to replace? We're trying to replace EMF, which is effectively electric potential, okay, potential difference. And we want to replace it with the electric field. You remember from the past, do we have any bridges, or did we introduce any bridges which connected electric field and the electric potential? Do you remember chapter 26? Immediately after the first midterm exam, where we learn how to move from the electric field to the electric potential, and how to move back from the electric potential to the electric field. So we just need to recall that and use one of those formulas. And we're going to use that 26.3. So you remember, that's how we moved from the electric field to the potential difference between this initial and the final point. So the potential difference, usually we would pick some path, and potential difference at the final point minus potential difference, minus electric potential. Okay, electric potential at the final point minus the electric potential at the initial point equals to the negative integral along the path between these 2 points. So we need to apply this formula for our case. And again, you remember, we are trying to replace EMF. EMF produced where? In the closed loop. So it means that if I, for example, start counting potential differences, EMF, if I start from this point, I have to move around the closed loop, around the whole loop, and I need to get back to exactly the same point in order to get our EMF, because you remember EMF is produced in the closed loop. So now, in order to apply this formula, what can you say about our final point and initial point? It must be the same point, this one, right? So this is our initial point, and then when you complete the loop, you'll come back to exactly the same point. That will be our final point, right? So in order to get our EMF out of this delta V, we need to integrate over the whole loop, right? And as a result, on this right-hand side of the equation, we're going to see integral over the closed loop. So we're going to see a small circle at the center of this integral. You remember the meaning of that circle in the middle of the integral? Integration over something which is closed. In this case, it's a closed loop, right? So instead of delta V, as a result, we have EMF, right? You see EMF. And that integral over the closed loop, E dot ds. Don't ask me about that minus, right? Forget about it. Usually books, I looked through several books, they usually try to move over that minus without discussing it. So EMF equals to integral over the closed loop of E dot ds. ds is the element of that of the loop. Okay, so that's what we can get from this formula, applying this formula for our particular case. But of course, according to the Faraday's law, EMF equals to negative rate of change of the magnetic flux minus d phi over dt. So now we can combine this with that integral, and we are getting the final, the most general form of the Faraday's law. Left-hand side, it's that integral over the closed loop, E dot ds, and the right-hand side, negative rate of change of the magnetic flux. So again, this is our EMF, and that is our right-hand side of our old form of the Faraday's law. So this is the most general form of the Faraday's law. You can open any book in physics, right, at the page about Maxwell's equations in an integral form, written in an integral form, and you will see, usually this is equation number 3. You will never see a physics book with the whole set of Maxwell's equations where EMF is used. No, every time it will be written in this way, in terms of electric field and magnetic field inside of this magnetic flux, right? In terms of fundamental quantities. Again, EMF, it's a very useful, ridiculously useful quantity, but it's more for people who work with applications, right? For physicists, usually it's an electric field and magnetic field. Right? Okay, so now let's look at the structure of this law. On the right-hand side, the rate of change of the magnetic flux. This magnetic flux, changing in time magnetic flux, is the source of what? Source of this induced electric field. So on the right-hand side, we have source, a source, and on the left-hand side, inside of the integral, we have a field which is produced by that source. We had very similar structure when we introduced Gauss's law, for example. You remember, integral over the closed surface, E dot dA equals to Q enclosed divided by epsilon naught. So again, Q enclosed, what is that? Sources, charges, sources which produce electric field, which is shown on the left-hand side of the equation. charges on the right hand side produces electric field, which is shown on the left hand side of the equation. Then Ampere's law, exactly the same structure. You remember, integral over the closed loop B dot ds equals to mu naught times I enclosed. I enclosed currents are sources of the magnetic field, which is shown on the left hand side of the equation inside of the integral. And now Faraday's law has exactly the same structure. On the right hand side we have sources, rate of change of the magnetic flux, and on the left hand side we have electric field produced by these sources. All Maxwell's equations have exactly the same structure. On the right hand side we have sources, on the left hand side we have fields produced by those sources, and of course all those fields all the time is shown inside of the integral. It's a very nice, elegant structure of all Maxwell's equations. Right? Okay, so now let's apply this Faraday's law for very, very special case in order to get to a tremendous conclusion after getting some water. So let's apply that, assuming that, for example, we apply for a loop which is area of which is constant, and let's assume that our angle is 0 in order to take care of the right hand side of the equation, minus d phi over dt. Right? So what will be the flux in that case? Flux, it's a dot product, and it will be in our case, if area is constant and angle is 0, it will be equal b times a. And as a result, let's rewrite Faraday's law for this special situation. Again, left hand side will be exactly the same, integral of E dot ds, and instead of d phi over dt, now we'll have a db over dt. And you remember I told you just now, on the right hand side we have sources of fields shown on the left hand side. So what is the source? dB over dt, rate of change of what? Magnetic field. So this is the source, and it produces what? It produces electric field. Changing in time magnetic field produces electric field. This is something tremendous, really tremendous at this point, because you remember, basically we started this semester treating electric field, electric world and magnetic world as two independent worlds, right? And you remember that Ørsted experiment which I discussed with you as a first example, where first case where people realized that there is a connection between these two worlds, between the world of electricity and the world of magnetism. And now we're realizing that electric field can be produced by the magnetic field. Probably for those people back then it was a mind-blowing sort of conclusion. Basically it means that these two worlds, electricity and magnetism, they're inseparable. They're so deeply connected that it's impossible to separate them. That's why it is called usually just electromagnetism. One field can be produced from the other one, right? Of course, changing in time magnetic field produces electric field. It's something really tremendous, something great. And that's why these guys keep jumping, and it will keep jumping until I move to the next slide, right? Okay, right. So, and that's what happened in the previous example, right? When we have basically uniform magnetic field, and if that magnetic field changes in time, electric field is produced, forming with electric field lines in the form of circles. Right? For example, if I have a solenoid, let's say solenoid, right? And let's assume that current through the solenoid is changing in time. Of course, what can you say about the magnetic field inside? It will be uniform, but changing in time, because current is changing in time. So changing in time magnetic field inside of the solenoid is going to produce induced electric field. Inside of the solenoid, we're going to have electric field lines in the form of circles. Again, whenever you see changing in time magnetic field, there must be induced electric field over there. That's how God programmed this world. We're just trying to model it, just trying to describe it, right? And that's what people observed, right? And that's how we model it, right? Okay, so now then you remember I told you about the two types of electric fields, right? And now let's just juxtapose their properties. Of course, I'm not going to ask on the exam about these properties, right, or compare properties of these two fields, but it's just for you, because at some point in high-level courses, of course, you will dive deeper, and so that you would be somewhat familiar with these ideas, right? Okay, so two fields. So first box, second box. This box will be about the old electric field. We can call it Coulomb electric field. And now the new electric field, the induced electric field, right? Okay, so now sources of the Coulomb electric field. Point charges, our electrons, protons, right? So produced by charges. And of course, Gauss's law describes that, right? You remember Gauss's law? On the right-hand side, we have the charges Q enclosed. And on the left-hand side, we have electric field. Coulomb electric field. So Coulomb, Gauss's law, of course, describes appearance of the Coulomb electric field. Then induced electric field is produced by what? Not by charges, but changing in time magnetic field. This you see, dB over dt. Changing in time magnetic field produces the induced electric field. So that's the source of the induced electric field, and sources of the Coulomb electric field, charges. Right. Second, about the electric field lines. You remember at the beginning of the semester, Coulomb electric field lines, they start on positive charges and end on negative charges. All the time Coulomb electric fields, they have beginnings and they have ends, right? Okay, you remember those pictures, right? Induced electric field, no beginnings, no ends. All the time they form closed loops. Of course, in ours, the nicest, the simplest situation, when we had uniform magnetic field, electric field lines formed circles. But of course, it doesn't have to be in general, right? So for complicated magnetic field changing in time, of course, induced electric field lines will have a complicated shape. But all the time, they must form closed loops, right? Okay, so yeah, that's the example, basically our example, which we just discussed like 10 minutes ago. And the last part, again, it's probably for most of you it will be confusing, but I just want to state it, and in some high-level classes you will dive deeper into that. So you remember Kirchhoff rule, Kirchhoff loop rule. Whenever you have a closed loop, right? You remember in a circuit. And if you start moving from, for example, from this point, or moving around, counting all the potential differences, you remember delta V's plus delta V1, delta V2 plus delta V3 plus delta V, and so on. Once you complete the loop, what we had at the very end? 0. All right? The total potential difference, if you add up all the potential differences around the loop, at the end, when you finished adding up, you must get 0. That was the case with the Coulomb electric field. But now, and of course that field was a conservative field. But now for the induced case, if you integrate over a closed loop, E dot ds, that's our EMF, right? And now it's not 0. It's minus a rate of change of the magnetic flux. As a result, this induced electric field is not conservative. Again, I will never ask you on the exam anything about this, but I just wanted to expose you to that, right? Because again, especially the last part, needs deeper explanations, right? But I just wanted to mention that these two fields are quite different. Okay, some properties are different, not quite different. Some properties are different. Okay, so and now in order to conclude this class at this exciting moment, so I created the separate slide. So again, our Faraday's law, right? One of the fundamental laws, right? And now you see that these fields are so deeply connected. Field of magnetism, field of electricity, right? So electric field can be produced by magnetic field. So pretty much it's sort of like these fields are inseparable, right? So that's why I created this picture, right? So sort of like an eternal dance of electric and magnetic field, right? Especially it will be impressive when we get to optics and we start discussing electromagnetic wave. That's probably the most spectacular system, the most impressive system, at least from my point of view, right? But of course, we will discuss that maybe in like 3 classes. And I think now we need to move to the very practical element. The next one. Inductors. New circuit element. And of course, properties of this element can be described by what we just introduced. And you remember I already mentioned several times about this element in the past when we were introducing capacitors, capacitance, then resistance, right? And I told you, guys, there are lots of similarities between these 3 elements, capacitors, resistors, and then in the future we will talk about inductors. So now we came to the point where we need to again compare now this element with previous 2. And as I told you, there are lots of similarities, right? So let's just first sort of let's introduce the main role of an inductor in a circuit. Right? You remember I asked you the same question when we were introducing capacitance, right? And I ask you what was the main role of a capacitor in the circuit, right? And you remember usually I told you usually students answer it allows us to store charge, but I corrected you, guys. It's better to pronounce it in this way. It allows us capacitors allows us to store energy in the form of the electric field. And now I'm going to introduce the role of an inductor in a very similar way. An inductor, it's a device or an element which allows us to store energy, but now in the form of a magnetic field. And you remember the same similar picture we had, but back then we had a capacitor, not an inductor over here, and again sniffing cat, right? And that's why I present their roles in the same in this way, because it's easier to compare them. It's easier to see similarities, right? So capacitor allowed us to store energy in the form of the electric field. Now inductor allows us to store energy in the form of the magnetic field. In both cases, they allowed us to store energy, and which can be used later, right? And that's why you can have with capacitors RC circuits, with inductors L circuits, right? Okay, so that's a general role, and now let's actually introduce the inductance, right? Strictly, right? Because we're all here science majors, and of course we need to introduce it using some formula, some expressions, so that we can be quantitative, right? Okay, so let's assume that we have a typical inductor. A typical inductor is a solenoid. Typical inductor, right? So let's assume that we have a solenoid with n turns. Current flows through the solenoid, right? Of course, the I don't know, cross-sectional area of the solenoid we assume is known. The length of the solenoid is known. So pretty much all the geometry we assume is given or known, right? And now let's look at this. So current goes into the solenoid. So from this side and leaves the solenoid from that side. So if there is a current, also inside of the solenoid, there will be magnetic field. And you see these blue vectors, magnetic field, uniform magnetic field inside of the solenoid. Sorry. If, or whenever you have a loop and magnetic field, of course, there is a magnetic flux. We have magnetic flux through one loop, but of course, solenoid consists of n loops. Of course, we can introduce the total magnetic flux. So if you take the flux through one loop, then flux through the second loop, then third, fourth, and so on, right? So if you add up all those fluxes, of course, you will end up with the total flux through this solenoid. So now let's play with these two quantities. On one side, at the very beginning, we have current entering the solenoid. On the other side, on the other end, we have total magnetic flux through the solenoid. Now let's play with these two quantities. What if we increase current? Obviously, magnetic flux should go up. If you increase current more, flux will go up more. And if you keep playing like this, creating like a bunch of lots of data, and then if you start looking at their ratio, it's just a normal desire whenever you see two quantities increasing at the same time. Of course, you want to see what about their ratio? Is it going to be constant or not, right? So, and if you start looking at the ratio of the flux versus current, you will be surprised, or maybe not so surprised, that ratio is going to be exactly the same within experimental error, of course, right? So if that ratio is exactly the same, for this particular object, for this particular solenoid, if you don't change it, then it means that that ratio is some kind of intrinsic property of this object, of this solenoid, of this inductor, right? And it makes sense to give it a special name, right? Cool name, so it would sound cool, and that cool name is inductance, and symbol L is used. So that's how inductance is introduced. It's a ratio of the total flux through the inductor divided by the current produce that flux. So that's by definition inductance is. And you see, in a similar way, we introduced capacitance. Capacitance was Q divided by delta V, charge divided by the potential difference. Then, in a similar way, we introduced resistance as potential difference divided by the current. And now, in a similar way, we introduced inductance as a ratio of the flux, now magnetic flux divided by the current. And, all right, so now we introduce a new quantity. And of course, then what do we usually ask after this? Should we introduce the special unit, special SI unit? And I think the answer is obvious. Inductance is used a lot in circuitry, right? In our, okay, not in everyday life, but in the world of engineering, right? Inductance is used a lot. So it makes sense to simplify their life a little bit, at least a little bit, right? And instead of pronouncing every time, it's a what? Weber units of flux, Weber divided by amps, Weber divided by amps. It's better to introduce something interesting, something cool. Henry. So units of inductance, Henry. So 1 Henry, as I said, it's just a 1 Weber divided by amps, right? Again, if something used a lot, then it makes sense to introduce something to make life of people who uses a little bit easier. All right, symbol in circuits, symbol which is used to show the presence of the inductance. It's just this sort of like a coil. So what's next? I think next is we need to discuss potential difference. Let me. No. That will be later. So next, all right. Look, this is definition in general. You can apply this definition to find inductance of any object. Any object. You can use that formula to find inductance of a solenoid, and that's what we're going to do. You can apply that, and you can find inductance of a piece of wire. Any object has some amount of inductance, right? Even as I said, this piece of wire will have some amount of inductance. So any circuit, right, have some amount of inductance, even if there is no solenoid over there, right? You can find inductance of me, but again, I'm not going to like if you start driving current through me, right? So I will resist, significantly resist, right? So the bottom line, you can find inductance of any object, right? Using this formula. So let's apply this formula to find inductance of a typical inductor of a solenoid, right? Because, yeah, we've been using solenoid a lot and we will continue using it, right? So let's find inductance of a solenoid. So let's assume that we have a solenoid with n loops, n turns, current I entering, over there current leaves the solenoid, right? Of course, there will be a magnetic field inside of the solenoid, right? So we assume that cross-sectional area is given. Then we will assume that length of the solenoid is given. So pretty much we know everything about the geometry of this solenoid, right? And we need to apply the formula which we just introduced. Flux, total flux divided by the current, right? So let's write down, let's find the flux, the total flux through this solenoid. Of course, the total flux will consist of fluxes through each loop. So if we have n loops, right, in the solenoid, of course, the total flux will be n number of loops times flux through one of those loops, right? So we can write it as n times phi sub 1. Phi sub 1, it's a flux through one of those loops. Then, how can we write this flux through one loop? Okay, so we can easily do that because we have magnetic field inside UCB. Area vector we can introduce any way we want, right? So we can position it this way or we can position it that way. So let's align our area vector along a direction of the magnetic field, along that B, right? So that dot product between B and A, angle between B and A will be 0, right? And as a result, dot product will be just a product of magnitude B and magnitude A, right? So that's flux through the through one loop B dot A. But again, if I assume that A is in the same direction as B, so A parallel to B. Of course, this formula can be rewritten as NBA, right? So that's the total flux, right? Yeah, like National Basketball Association, right? NBA. Yeah, so now you know what NBA is. It's just a flux. Sounds so insulting, right? All right. Okay. Anyway, so that's the expression for the total flux. But we can dive even deeper. Okay, and yeah, it's a given. Area, cross-sectional area is also a given. But we can dive inside of the magnetic field. We can write magnetic field in terms of some other quantities. And you remember that is your flux. That is your quiz number 5, the previous quiz, right? You remember you derived an expression for the magnetic field inside of the solenoid. Right? And it was mu naught B inside of the solenoid, mu naught, our universal constant, times n, it's a number of loops per unit length of the solenoid, right? N times the value of the current. Right? So we can take that and shove it in our NBA. Right? And of course, we can also write n small number of loops per unit length as total number of loops divided by the length of the solenoid. Just my computer was just showing me some messages, so it distracted me immediately, right? Right. So now we can shove it into the our expression for the total flux. So we can plug it over there, and as a result, we'll get the total expression for the total flux. So phi equals n. Then instead of B, we have that mu naught n divided by L times I, n times area. Area, cross-sectional area of the solenoid. Okay, pretty much we're almost done. Now let's just make it look nice, because we have two n capitals, so it will be n squared. So let's just arrange these factors properly. So it will be mu naught n squared a divided by L, and our current I on purpose wrote separately. And so now let's recall the definition of inductance. It's the flux divided by current, which is over here. So let's just take this current to the left hand side, and as a result we'll get the expression for the inductance over solenoid. Pretty much this factor, this construction in front of the current, that's our inductance over this solenoid over solenoid, right? And okay, let me frame it, right? And now the question which I asked you when we were introducing capacitance over parallel plate capacitor, and then the resistance over some cylindrical resistor. What's the major feature of this formula? What's the major feature of this formula? Does it depend on, for example, I don't know, magnetic field? No. Does it depend on flux? No. Does it depend on any other magnetic or electric quantities? Nothing like that. It only depends on what? Mu naught. Basically, you remember mu naught, it's that universal constant which describes magnetic properties of vacuum. If this space in the solenoid were filled with some material, then of course instead of mu naught we would have mu, which constant which you can get from the reference book, right? Okay, so pretty much mu naught describes the material inside of the solenoid. Then n, number of loops, it's a geometry. A, cross-sectional over solenoid geometry, and divided by L. What is L? The length of the solenoid. L is the length of the solenoid. You see, pretty much L capital inductance depends only on the geometry of our solenoid. That's why if you build a solenoid, if you build this inductor in your garage, you can label it immediately, right? So you see lots of similarities between these three elements: capacitance, resistance, and now inductance. Even the formulas for a parallel plate capacitor, and then the cylindrical resistor, and now solenoid, inductance over solenoid, they have similar properties. They all depends only on the geometry and the material, right? So that's why if you build them, you can label them. You can measure all these parameters, right? Calculate this, and that will be the inductance. Okay, so now what else? Yeah, that's what I just told you. What else? Yeah. Next, we need to discuss potential difference across a capacitor. Across the inductor. Monday morning, right? 8 a.m. So my brain is still waking up. Potential difference across an inductor. And you know what? Every time when I get to this point, it blows up my mind, right, to some extent, because it's sort of so spooky, right? I don't know, right? Mysterious. Because what are we asking for? We're asking about potential difference across an inductor. Let me just finish my thought, and then after the break we will continue this. What is so surprising for me? You remember in the past, when did we see any potential differences? If you have a resistor, for example, right? If you have a resistor, then if current flows through that, right? So it gives us potential difference, right? Because there is a resistance. Then battery, it's an active element, right? So chemical reaction inside. As a result, we have a potential difference across a battery. But how can we get the potential difference across a solenoid? Because what effectively the solenoid is, it's just a piece of wire. And most of the time we assume it's an ideal piece of wire. It means that it doesn't have resistance. Why would you expect to have any potential difference across an ideal piece of wire which doesn't have resistance, which doesn't work as a battery? Why? Why would you get any potential difference across this device? But if you take your wire, wrap it around some cylindrical surface, and now, under certain conditions, you're going to see the potential differences across this device. Basically, I just created a solenoid. But again, if I unwrap it back to a straight piece of wire, you're not going to see any longer any potential differences across this device. It's pretty much the same piece of wire, but if you present it like in this shape, no potential difference. But if you wrap it, you'll start seeing potential difference. Spooky, right? It's mysterious, right? But of course, the thing is, of course, this can be explained, and of course, after the break, I will explain it. Of course, now we'll have to use Faraday's law in order to explain this process, right? And that's why we introduce inductors after introducing Faraday's law. Because you remember, according to the Faraday's law, if magnetic flux through the loop changes, then EMF is produced, potential difference, and current is produced, right? So pretty much that EMF is responsible for the production of the potential difference across this piece of wire wrapped in this form, right, across the solenoid. Yeah, I know physics, right, to some level, but every time when I get to this point, it surprises my brain. Okay, anyway, so now, again, let's assume that we have a solenoid, typical, okay, solenoid as a typical inductor, right? Again, what we want to find? We want to find the potential difference basically between endpoints, right? So if current enters through this point, leaves solenoid from this point, so this is our final point according to the current direction. So this is our final point, and that is our initial point. The point where current enters is initial point. The point where current leaves, that's our final point. So delta V, it's a V final minus V initial. That's what we want to find. And as I said, we cannot explain this potential difference using anything from the past except for Faraday's law. Faraday's law is responsible for this potential difference which can be produced. So EMF equals minus rate of change of the magnetic flux. And now, of course, at this point, you can start screaming at me. So how come that I'm trying to use the formula which we used all the time where? For a closed loop, just for a single closed loop. And now we're trying to find the potential difference between these endpoints of the solenoid, right? But the thing is, yeah, we can apply that Faraday's law for each of these loops because solenoid consists of, for example, several hundred or several thousand identical loops. Right? So of course, I can apply that Faraday's law for each of these loops. For example, the loop number 1, I can get EMF1 equals to minus d phi 1 over dt. Then I can grab the second loop, exactly the same. It will be EMF2 equals to minus d phi 2 over dt. And so on. I can create, I don't know, a few thousand equations like this, right? EMF1 equals to, EMF equals to minus d phi over dt. And then if I add all those equations up, of course, d over dt can be basically like factor out, and we will get the total flux, right, through the solenoid. And over here, if you add all those EMF1 plus EMF2 plus EMF3 plus till EMFn, so if you add them all up, you will end up with the potential difference between the final points and the initial point, right? So that's why I can still use this equation, and now this EMF is just a potential difference across this whole solenoid. It's basically V final minus V initial. And this phi, it's the total flux through the whole solenoid. All right. Okay, so that's why I can just, it looks like I just grab Faraday's law, but of course we need to understand what we actually do, right? Okay, so yeah, as I said, now it's just our delta V because this is EMF produced by our N loops, right? And the total flux, so how can we write the total flux? We just introduced the inductance, all right? Inductance was introduced using the total flux. So my explanation box, right, and you remember the definition, L equals phi over I. So of course we can solve it for phi. Phi equals the product of the inductance of your inductor or of your solenoid times current. And so now if you just shoved it into this time derivative, L is the constant. Usually, if you build an inductor, right, so you know the inductance. So inductance basically some given constant, right? Again, if geometry is given, so basically you can calculate that. Inductance is basically given. So of course, it doesn't depend on time. So of course, you can take it outside of the sign of differentiation. Right? So you will get minus L di over dt. So that's it. That's the derivation of the potential difference. And so now let me just write it separately, frame it, and now let's look at this formula very, very carefully, because lots of physics inside of this formula, right? So just a potential difference across an inductor. And now I will move to the next slide, and we will look at this formula again, as I said, very, very carefully. Because yes, students don't have any problems applying this formula, but interpreting, sometimes answering conceptual question, which is based on this formula, lots of students have some problems. Okay, so first of all, I just copied and pasted formula. First of all, what is so interesting about this formula? That this potential difference, right, potential difference, does not depend on the value of the current. It doesn't matter how strong your current is, 1 amp or 100 amps. No, it doesn't care. Potential difference doesn't care. What it cares only how fast current changes in time. It can be a very small value of the current, but if it changes significantly, then delta V will be significant. But if your current is gigantic, let's say 100 amps, but if it doesn't change in time, then potential difference will be zero. So you see, potential difference does not depend on the value of the current, but it depends on how fast that current changes in time, right? So if current is constant, then there wouldn't be any potential difference across the solenoid. In this case, your solenoid doesn't do pretty much anything in the circuit if current is constant. In a DC circuit, a solenoid in an inductor is just a useless piece of long wire, nothing else. But interesting effects happen when current changes. So when current changes, solenoids can be and inductors can be very, very useful. So now let's see what are we going to see across the solenoid if current changes. So let's start with the first situation. For example, what if current is increases? I was trying to recall what's the first case. Current increases. So current increases in time. I know, let's say 3 amps, 4 amps, 5 amps, and so on. If current increases, so what can you say about DI? DI positive, right? And of course, DT cannot be negative. Come on, time just goes forward. We cannot change direction of time. So as a result, DI over DT is positive, right? Of course, DI over DT is positive. So now DI over DT is positive. Then there is a minus in front. So it means that what can we say about delta V? Delta V is negative. Again, di over dt is positive and minus in front, so it means that delta V is negative. So what does it mean? It means, again, by definition, what is delta V? It's a value of the electric potential at the final point minus value of the electric potential at the initial point. By definition of delta, all the time, final minus initial. Right? So it means that electric potential at the final point is smaller than the electric potential at the initial point. And we just discussed which point is initial, which point is final in the solenoid. It's according to the current direction. If current leaves this point, at this point, that is our final point. If current enters at this point, that's our initial point. Okay, so now let's just draw a simple oversimplified circuit in order to understand what we got and what's the conclusion. So let me open the circuit like this, oversimplified. Just let's assume that we have a solenoid connected directly to the battery. Not very practical, but who cares? We just want to discuss what we just got, what we received. So this is a battery, or the battery, which produces this original current, which changes and which increases. So that's original current produced by that battery. So let me draw this using this blue line. And again, original current. Now, what's the response of the solenoid to the fact that this current increases? This solenoid starts producing this potential difference across itself. And so, in such a way that the final point, so the final point is that point, right? I'm trying to reach it. So that point has smaller potential than the initial point, right? So pretty much it means, okay, yeah, again, that is our final point, that because original current leaves the solenoid at this point, and this is our initial point, right? Because current enters. And according to our calculations, now electric potential at this point is smaller than electric potential at this point. So you see, that's why I put there minus. Minus means smaller, plus means higher, right? Okay, so and that is produced by the solenoid. You guys, at this point probably I should pause for a second and emphasize on this, right? So this battery produces its own distribution of potential, blah blah, right? So it's its own work. But this plus and minus, it's done by this solenoid. It's basically like, I don't know, now most of the goods are, have a stamp made in China. So now we can stamp on this delta V, on this VV stamp made by the solenoid, made by the inductor. Of course, you can ask me the question, so how come that this inductor can produce its own potential difference? Where is the energy, right? Where is the energy? Who pays for this fun? You remember the first slide of this when I started presenting inductance? You remember what was the main role of an inductor in a circuit? It allows us to store energy in the form of the magnetic field. So since there is a magnetic field inside of that solenoid, there is some amount of energy. And that solenoid is free to spend that energy any way it wants. So in this case, the solenoid spends that energy to produce this additional potential difference on top what this battery produces, right? Again, I emphasize that this V final and V minus delta V is produced by this solenoid using its internal energy, internal resources, right? Okay, so that's what solenoid produces, right? And so as a result, I can say that this solenoid starts working as a small, effectively as a small battery. And that's why, you see, I sort of position a small symbol of a battery. And of course, there's no battery. But in order to simplify a number of mistakes, I will explain in a second why. I decided at some point to introduce this small battery and pronounce it a small, effectively small battery. Starts working as small battery. Why? So now this battery with this polarity, plus on this side, minus on that side, of course, it will drive its own additional induced current. In which direction? From plus to minus. So if this solenoid works as a battery, of course, it will drive the current through the rest of the circuit from this plus to that minus, right? In the direction opposite to the direction of the original current. It's an induced current. Effectively, It's all those discussions which we had on in a previous class, finding the direction of this of that induced current. It's that induced current, but now applied for a more complicated system, for a solenoid, right? So now in this case, that solenoid will drive the current in the direction opposite to the direction of the original current, right? And now let me state the rule. In order to find a direction of this induced current, right? Again, effectively, it's a Lenz's rule behind all this, right? Of course, we can make a transition from that Lenz's rule to this system, but application of the Lenz's rule in this particular system, for a solenoid, it's not the most convenient. It's better to restate it in a slightly different form, right? In a slightly different form, but although it's just basically the same Lenz's rule. So new form of that Lenz's rule applied for this situation. Now we're going to state in this way. Solenoid is our system, is our object. And you remember, any system in the universe doesn't like changes. So now, solenoid. What solenoid doesn't like? Or changes in what a solenoid doesn't like? Solenoid doesn't like changes in this original current, blue current, which flows through the solenoid. The solenoid doesn't like changes in this blue original current. As a result, every time it behaves like that loop in the Lenz's rule. So if the solenoid sees that current increases, it doesn't like it, and in this case, it tries to rebel. It starts producing its own potential difference, this potential difference which we just discussed, in such a way so that induced current will flow in the opposite direction to the direction of the original current, trying to suppress the growth of the original current because it doesn't like changes in the current. You see, basically it's sort of like a Lenz's rule, but now restated in a slightly different form, right? So the solenoid doesn't like changes in the original, that blue current. And if that current increases, like that's what we've been discussing, right? The solenoid rebels and it starts driving current in the opposite direction, trying to suppress the growth of the original current, right? And we observe that. Typical example, or maybe, yeah, the typical and the most simplest example. So let's imagine this situation. Let's say you have some arbitrary circuit, electrical circuit, right? And let's say first the switch is open. So the switch is open, and of course, there is no current in that circuit. But let's say at this point, at this moment of time, we close the switch. And of course, current starts flowing through the loop, through the circuit. And of course, if you don't know physics deep enough, if you don't know this physics, you would expect that just current will just jump from 0 to, let's say, 1 amp, right? And then it will be constant. But in real life, it doesn't happen. Because, as I told you, any piece of wire has some amount of inductance. And if your circuit has some inductor, right? Then that inductor is going to behave like this. So it sees that current start changing very fast through that inductor, right? And of course, inductor is not going to like it, like what we just discussed, right? So it sees current increases, and of course, immediately that inductor starts producing potential difference, its own potential difference, in such a way that the induced current will flow in the direction opposite to the direction of the original current. And as they're suppressing, so that current, original current, wouldn't grow that fast. As a result, instead of this step function describing the current through the circuit, you're going to see something like this. Current is going to increase slowly. Nature doesn't like sudden changes. Nature doesn't like step functions. Every time there will be some two battling mechanisms, right? As a result, there will be some smooth transition, right? So that's what we're going to see, right? Because pretty much, as I said, any circuit has some amount of inductance. As a result, that inductance is going to slow down as a result every time you you can, I don't know, connect an oscilloscope, right, and see. You will never see a step functions, right? If you zoom in properly, you will see that no, voltage potential difference current increases over a finite period of time. Nature doesn't like step functions. Right? Okay, so that's the first part when current through the solenoid increases. Now let's look at the second situation. What if the original current decreases? And now you can guess what we're going to see, right? So current decreases. So now di is negative, dt is positive all the time. You cannot force time go back, right? It's only in Hollywood. It's only possible in Hollywood, right? In the movies like Back to the Future. Right? So anyway, so as a result, di over dt is going to be negative. Di over dt is negative, minus in front of the whole structure, the whole formula. So that minus and that minus are going to give us plus. As a result, delta V is positive. And again, we know which point is final, which point is initial. So it means that V final, electric potential at the final point, is going to be larger than the electric potential at the initial point. Now let me open a very similar picture in order to see what will happen in this simple circuit. Again, I will show this oversimplified diagram. So we have a battery, original battery, which drives original current through the solenoid. Again, that original current I will show using the blue line, right? Original current, which creates all this mass. And of course, current, which here decreases, all right? So, and V final now is larger, electric potential is larger, at the final point is larger, the electric potential at the initial point. Again, that is our final point because that's where current leaves this solenoid. That's final point, that is initial point, right? So it means that now at the final point we have plus, and at the initial point we have minus. Here we had what? Minus and plus. Now we have opposite polarity. And again, that's the potential difference produced by the solenoid using its internal resources, energy stored inside. And again, so in this case, like in the previous situation, it was it rebelled, right, driving current in the opposite direction. But of course, since our resources, that internal energy has limited amount of energy, of course it will rebel for some short period of time, and then eventually, of course, the original current will win, right? And so it's not going to rebel forever. So yeah, so that's the now that's what solenoid produces now, plus minus. And again, I will introduce that small, effectively a small battery, right? Oops, you know what? Something happens and that's my small battery disappeared. Okay, but anyway, I just only now I noticed, right? Maybe I made some changes, right? And probably it went behind other pictures here. Right. But anyway, so of course, now it starts working a small battery with this polarity, plus on this side and of course minus on that side. And of course, now it will start driving induced current in the same direction as the original current, right? From this plus, to that minus, but of course through the rest of the circuit. So now induced current is going to be in the same direction as the original current. So now we can develop, or now we can present the rule, which is again effectively Lenz's rule, but restated for this particular situation. So if, no, probably should I state, since solenoid doesn't like changes in the current, so that's the original. Doesn't like changes in the current. So in this case, current what decreases, current decreases. Current is going down, so the solenoid is not going to like it. So as a result, it becomes supportive, like Florence Nightingale. Remember those words. As a result, it will produce the potential difference like this, right? And as a result, the induced current is going to flow in the same direction as the original current, supporting dying current. Right. So, example, again, similar to this one. So let's assume that we have some circuit with some constant current, right? And let's say here there is a switch. And let's say at this moment of time, I open the switch. Of course, if you don't know this physics, right, you would expect that the current will just drop dead, right, to zero, right, instantaneously. But again, nature doesn't like sudden things. It doesn't like sudden changes. Every time there's some couple of battling mechanisms, right? In this case, since any circuit has some amount of inductance, even if you don't have an inductor, any piece of wire has some amount of inductance. So that inductance will behave this way. So that inductance sees that original current is dropping dead, basically, right? Trying to change itself very, very fast. The solenoid, the inductor, is not going to like it. So in this case, it becomes supportive like Florence Nightingale. So as a result, it uses its internal energy and it will start driving induced current in the same direction as the original current, supporting it, helping it live longer a little bit, right? So as a result, instead of this step function, we will have something like that. So real current will just decay over some finite period of time. Again, nature doesn't like sudden changes, right? I don't know why. God created nature this way. We're just trying to describe. And okay, so I wanted to say now why I usually introduce this small effective battery, because there's a typical mistake. When usually pictures on the picture, this solenoid are big, right, like here, right? And when they see that on this side it's plus, on that side there is a minus, they will try to drive the current in the wrong direction. So they remember, of course, current goes from plus to minus, so they just drive the current from this plus through the solenoid to that minus. No, this plus and that minus are produced by this solenoid, inside of this solenoid, and then current will flow from this plus to that minus through the rest of the circuit. So through the rest of the circuit, right? Not through the solenoid. Solenoid produces this plus and minus, and then current will flow through the rest of the solenoid. So basically, in order to reduce chances for you to make this typical mistake, I usually basically shrink this solenoid, this inductor, to a very, very small battery. So you wouldn't have a space, you wouldn't have a desire to drive the current in the wrong direction. Before I didn't use this battery, but then after seeing this typical mistake over and over, I started introducing this battery, right? So that you would drive current in the correct direction. Okay, so that's basically, again, application of the Lenz rule for this, or Lenz rule adjusted for this system, because it will be more convenient to analyze the system using this rule. And of course, the last situation, which I already mentioned, if current is constant, the solenoid will be just slipping. It will be just a useless long piece of wire. But if current changes, then we can see this phenomena, which are very, very useful. Right? So now that's what I was planning to discuss. And now the question for you, based on what we just discussed. Two solenoids, two inductors. The first one, inductance L, 2 Henry. Inductance of the second solenoid, 1 Henry. Then there is a current I1 flowing through this inductor, through this solenoid. Something happens in time to this inductor. We don't know what. But we see the response of the solenoid. You see, the solenoid feels the changes in this current, and as a result, it produces higher potential at the end, lower potential at the beginning, at the entrance, right? In the second situation, again, something similar. Something happens to this current I2, and the solenoid responds with higher potential at that point and lower potential at the beginning. So, question is, which current, I1 or I2, changes more rapidly? And the question is just basically about absolute value. We don't care if current right now decreases or increases. The question is about just which current changes faster, right? And then, okay, of course, I will discuss it first conceptually, and then, of course, we will get numerically, right? So the question, of course, as usual, is in the chat. Let me switch to the chat to see your responses. Okay, it looks like a number of answers is not growing anymore, so it means that I can discuss. Okay, first I want to discuss conceptually before I start using these numbers. I just want to know what happens to these currents, current I1 and I2, in terms of in terms of time. Are they growing or are they decreasing in time, right? Okay, so current flows this way, so that is our initial point, and that is our final point, and we see that the final point is at higher potential. Initial point is at low potential. Again, these potentials are produced by the solenoid. So as a result, what is the direction of the induced current, right? So again, I can introduce a small effective battery over here with a positive electrode on that side and negative electrode on this side. So of course, that battery will start driving an induced current, a secondary current, and it will go also up, right, in the same direction as the original current. So induced current will flow in the same direction as the original current. It happens when? When does it happen? It happens when the original current is dying, right? It's the second case which we discussed in the previous slide, right? So if original current is dying, then the inductor, the solenoid, becomes supportive and behaves like Florence Nightingale, helping dying thing, right? In that case, currents are in the same direction. So it means, since current is going to flow in the same direction as the original, it means that the original current is decreasing. So I1 is decreasing, right? And the same we can see in the second case. Again, we see the response of the solenoid, plus here, minus there. So it means that induced current will flow again through the rest of the circuit in the same direction as the original current. And again, it happens only when the original current is dying. So in this case, the solenoid becomes supportive. So I2 is also going down. So both of these currents are decreasing in time, right? And so now let's actually answer the question, right? Answer the question. So the question is about di over dt, basically, right? How fast currents changes. So we just need to solve it for di over dt. So L goes to that side, right? And slides. I need to bring my slides forward, right? Right. And so di over dt equals minus delta V1 over LL, right? Actually L1, because we have different inductors, right? And so it will be equal to what? Minus 2 divided by 2 volts divided by 2 henries, right? And in the second situation, in the second case, it will be very similar, but now delta V is 4 volts and L2 is 1 Henry. So in this case, we have minus 1 volts per Henry or amps per second, right? In this case, it will be minus 4 volts per Henry or amps per second. Since the question is about only the absolute value of the changes, so of course, the second current changes faster, more rapidly. Second current, I2, changes faster. Right. And we know actually what happens, right? So current's decreasing, and we got it also mathematically. You see minus in front tells us that both of these currents are going down in time, changes in time, decreases in time. Okay, great. So that's the question, and I think now it's time for me to switch to the whiteboard, and we still have some time to solve a couple of problems.